Good afternoon, everyone. I'm Serena BOLIS from Lambda-X, and today I'm going to talk about ultra-compact optics for space exploration. After a short introduction about Lambda-X activities, I will briefly introduce the space environments, its peculiarities, and the constraints on the hardware that are dictated by this environment. And finally, we will see some of the examples from Lambda-X instruments. Some of them are already in space, and some of them are under design and assembly. So one of the main activities sector of Lambda-X is space, and this includes different sectors: microgravity, in-orbit servicing, Earth observation, and space exploration. Today we're going to focus on the last one, which is a space exploration. So let me start with a brief introduction on what is the space environment and what are the constraints that are dictated by this environment on the hardware. So first of all, space is quite far above us, and that means that we need launchers to escape Earth gravity. And that means that we want to build structures that are as light and as small as possible. This is because we want to reduce costs at launch, simply, but also because, for example, we want to reduce the power that's needed to power up the system once they arrived at their destination. Also, the instruments need to survive launch. That means that need to be designed in order to resist vibrations at launch, but also to resist, for example, shocks at landing, if it's applicable. The second factor we need to take into account is temperature. So typically, instruments in space are subjected to very large temperature gradients between the parts that are exposed to the sun and the parts that are in the shadow. Also, there is no or very little convection in space to dissipate the accumulated heat. So these constraints translate into the design, obliging us to design thermal structures, which means that these devices have performances that does not depend on the temperature, or that we need to shield our system in order to protect the most sensitive parts of the instrument. Also, typically, these devices are subjected to very strong thermal cycling between night and day, for example. And this thermal cycling can age and deteriorate the performances very quickly of the instrument. The third factor is vacuum. Of course, we are in outer space, which means that we are in ultra-high vacuum, which is around 10 to the minus 12, 10 to the minus 11 millibar. And in this environment, materials tend to outgas, which means that they tend to liberate contaminations that have been trapped on the surface or on the bulk of the material, or they can outgas materials that compose the materials itself if it's not designed to be used in vacuum. This contamination can be very detrimental for the instrument, because if it's deposited on sensitive surfaces or on devices or sensors, it can degrade the performances. But it can also be trickier than that. If that gas material is one of the materials that we want to detect, for example, water or organic materials, that means that we could have false positive due to this outgas. So this is why the integration is done in clean room environment, where we can control the particulate and molecular contamination of our system. The last factor I'm talking about is the radiation. Indeed, in space we can have quite high radiation levels, both electromagnetic and particles. And this radiation can damage instruments, but also materials and coatings. For example, for optical materials, the radiation can darken the glass, which means that the transmission is decreased and the performance of the instrument is degraded. This is why materials need to be selected in order to be radiation resistant according to the specification of the different missions. All these factors are already quite difficult by themselves, but we also have what's called the synergistic effect, which means if two of them are presented at the same time, the effect is more than the simple sum of the separated effect. For example, if we have an outgas material on a surface and this surface is subjected to UV radiation, for example, then we can have that this contaminant with the bulk can react and form a new component that can change, for example, the thermal properties of the material. So, having all this in mind, we can have a look at 3 examples from Lambda-X experience. 2 of them are already in flight and 1 of them is under design. The first mission I'm going to talk about is the ExoMars 2016, which included the Trace Gas Orbiter. This mission was an ESA-Russian joint mission, and the purpose was to send an orbiter around Mars in order to study the atmosphere and the surface of the planet. This mission was launched in 2016. It has arrived there at final orbiting by 2018, and it has been transmitting data since then. The spacecraft included different instruments, spectrometers, cameras, and detectors, and Lambda-X in particular was involved in one of them, the NOMAD instrument. NOMAD stands for Nadir Occultation for Mars Discovery, and it's a cluster of 3 spectrometers, 2 in the infrared and 1 in the UV visible. Lambda-X was responsible of the design, the assembly and the testing of this UV visible spectrometer. The purpose of this instrument was to identify and study the trace of gas in the atmospheric composition of Mars. The instrument was designed to work between 200 and 650 nanometers with a resolution of 1.5. And as you can see in the pictures, it was characterized by a very compact structure. For 700 grams and let's say half the size of the shoebox, we had a very sensitive and high resolution spectrometer. Here we can see the internal part of the spectrometer before it was closed in the final envelope. And here it's possible to see the entry of the spectrometer once it was mounted on the spacecraft. We had the pleasure to hear back from it with some recent publications in which it was shown that the UV spectrometer was used to detect green light coming from the daylight atmosphere of Mars. And it was possible to understand the origin of this light, which is believed to be due to atomic oxygen in the Mars atmosphere. The second mission I'm going to talk about is the JUICE mission, which stands for Jupiter Icy Moon Explorer. It's an ESA mission, and it aims to study the Jupiter complex environment and to study 3 of its moons, Callisto, Europa, and Ganymede. These are particularly interesting because they are water-rich bodies that can be a good environment for life. This mission has been launched this year in April, and at Lambda-X we all followed with quite some excitement the launch. And it is expected to arrive at Jupiter by 2031. The contribution of Lambda-X to the mission was with 2 monitoring cameras, the optics of these cameras. These are characterized by a very large field of view and the depth of field that goes from 1 meter up to infinity. They're designed to work in the visible, and the size is very small, so we're talking about more or less 5 by 5 by 5 centimeters. They're designed to work in a quite large temperature range, but the most striking specification was the resistance to radiation. So Jupiter is one of the let's say, hardest environment in terms of radiation level in the solar system, because it has a very strong magnetic field, which basically acts like a giant particle accelerator. And so instruments that stand there needs to be stand high level radiation. So this objective was designed with radiation resistant glass, at least at the outer part of the optics, and the internal parts were shielded with the metal of the external structure. Here it's possible to see one of the two cameras, kind of possible to see one of the two cameras once it's mounted on the spacecraft. But in order to understand better the purpose of these two cameras, it's easier to have a look at the schematic of the spacecraft. So here we can see the JUICE spacecraft, and the two cameras are the ones indicated in red on the spacecraft. They're looking at different and some of the most critical components at the external part of the spacecraft. The camera number one, the one on the left, it's looking at part of the solar panels and, among other things, to one of the antennas once it's deployed. While the camera number two is looking through the same antenna and when it's still stored. These cameras have been working since launch, and they have been monitoring the different steps of deployment of the spacecraft. So we had the pleasure to see some of the images transmitted from them quite soon, where it's possible to see part of the spacecraft and the Earth still behind soon after launch. Is also released a series of images where it's possible to see the deployment of one of the antennas, and the same image is possible to see on the bottom part, the solar panel once it was deployed. The last mission I'm going to talk about is the Mars Sample Return mission. As the acronym says, it's a mission aimed to go to Mars, collect some samples and bring them back to Earth. It's an ESA-NASA joint mission, and given the complexity of the objective, it has been separated in 3 phases. The first one is the Mars 2020. It's already ongoing. It's the one that brought the Perseverance rover on Mars, which is already collecting sample there. The second phase is the Earth Return Orbiter, which is going to send an orbiter around Mars, which is going to wait for the sample coming up from the surface, and which is also responsible to bring the sample back to Earth. The third phase is the sample retrieval lander, which is a lander that's going to be sent onto the Mars surface. It's going to fetch the sample, store them, send them up to the orbit of Mars, where they can be collected by the orbiter. So the first phase is already ongoing. The next 2 are planned for 2027 and 2028. And the samples are expected back to Earth by 2033. Lambda-X is currently involved in 2 of these phases, the orbiter and the lander. Let's start from the first one. So in the orbiter, Lambda-X is in charge of the optics of 7 monitoring cameras, which are going to be mounted on the external part of the spacecraft, and they're going to look at different angles of it. They are characterized by a quite large field of view and a depth of field that goes from 1 meter to infinity. The qualifications require a quite large temperature range and a quite important resistance to radiation. So these optics are currently under assembly, so the engineering models are being assembled. And the second part of the second contribution to the mission is with 2 optics for the 2 navigation cameras, which are going to be mounted on the robotic arm, which is going to look around, recognize the samples on the surface of Mars, go there, pick them up, and store them in the lander. So they are characterized by a smaller field of view and a depth of field that is shorter, down to 1 meter. The qualifications are fairly similar to the one for the monitoring cameras. The big difference is the fact that in this case we're going to land on another planet. So this means that we have to pay attention to not contaminate this planet with some biological materials. So in our case, this translates in the fact that these optics need to be sterilized, in this case by temperature, around 144 degrees for 2 weeks, in order to be sure to not have biological material that can contaminate Mars. And these 2 optics are currently under design, so we are in phase B. Coming to an end of my presentation, the space environment can be a very difficult environment for instrumentation, and this dictates quite a lot of constraints on the hardware. Lambda-X is a trusted and active partner in this field. Thank you very much. So you are welcome to ask questions if you like. I cannot really read it. So how do you test that an optical material is resistant to radiation? So yes, usually what happens is that you receive a specification, like for example in our case for the JUICE mission it was 40 megarat, and then you take sample of the material that you want to test, so like planar windows, and you put them in an environment where you can control the radiation absorbed by the material. So in that case it was in a radiation pool where there was a cobalt source at the bottom, and the samples were at a certain distance from the radiation source. And the sample was left there. It was in a small envelope, of course, to not be wet and so on. And they were left there in order to accumulate as much as radiation as the one that was asked for qualification. And then the transmission of the glass was measured before and after the tests, and it was compared in order to check that the losses were not too high. So, are there any missions foreseen for the Earth-Moon exploration? Yes. So there are a few rovers that are going to be sent soon to the Moon. In the first case, it's for a probe for the Prospect mission, which aims to go to a part of the Moon where there is expected to be found some water, and this rover is going to drill on the surface and remove some sample and analyze it. And the optics we're going to send there is going to be mounted on the camera that's mounted on the drill on the rover. For the MSR STA, are the navigation cameras intended for human control actions? No. So the collection of the samples is completely automatic. So the samples are stored in tubes with targets that can be recognized by an automatic way by the cameras, and the robotic arm is automatically driven to them, and it's trained, let's say, to pick them up and store them in the lander. Okay, thank you very much for listening.